Hi everyone. So my name is Georgi Manucheryan. I'm at the University of Washington, and I'll present a talk about our discrete element CIS model called SubZero. Uh, so let me share this presentation. So just a little bit of context. So this model development as well as analysis of various types of projects surrounding this new model is sponsored by the Office of Naval Research, the MURI program called Mathematics and Data Science for Physical Modeling and Prediction of Sea Ice. So it involves multiple universities, but the development of model is done at the University of Washington. So I'm leading the effort together with Brandon Montemuro. So what's the premise of the study? The idea was that existing flow models, flow scale models, were not overly representative of what the true picture of sea ice is. So, for example, if you look at over here, there's a huge amount of just a huge complexity of various flow shapes and their interactions and various types of fractures. And it just our CIS modeling community is not ready yet to to go to such high scales, even though a significant amount of efforts are being devoted at the moment to represent, to provide some sort of models of such granular type media. And this is why we're having a workshop to just bring people together to figure out what kind of new ideas are coming out of this research. But I think all of us could agree that continuous models cannot represent this kind of dynamics because it is inherently a sort of discontinuous, chunky type dynamics. So this is why discrete element models have advantage, and I will tell you about our model called SubZero and how it tries to overcome the disadvantages of continuous modeling and try to bring into some sort of unique physical solutions. Um, so just some very brief introduction for I guess, which is not necessarily needed for our workshop. But if you look at CIs on various types of scales, like this scale is a Bayesian scale over here, and if you look at very coarse resolution, the CIs could behave like some sort of continuous media. However, as you keep zooming in, now we're looking at the buffer gyre sort of region over here. Uh, you start seeing quite a lot of leads over here, and some fractures and some very nice flows forming already in between of those fractures. And if you keep zooming in even more, you will start seeing, let's say this is at a scale of 100 kilometers in a Fram straight, start seeing some distinct chunks. Now, of course, these are two different dynamical regions, but nonetheless, you start seeing what's the problem here, right? So is that the problem is that we have flows which are gigantic in size over here, and they behave for some time as a sort of more or less rigid body before they get fractured into pieces by various types of forcing, including waves from the ocean, but also due to collision between the flows. And also you have a huge number of smaller pieces over here. So this form the so-called flow size distribution that people tend to quantify quite a lot in CIs. But of course, reproducing this kind of image over here or over here with all its details is a very challenging task, and this is what a model will aim to do. Um, so looking at sort of different dynamical regimes, maybe we have a sort of 100% concentrated CIs, which is let's say in winter, or close to 100% concentration. This is a SAR snapshot, which shows that various sort of ridging patterns in the sea ice. And you also have a sort of a fairly weak sea ice in marginalized zones. So during summertime, where you have lots of sort of holes in between the chunks of ice, and they're not perfectly welded together pieces, but they continue to fracture all the time, and there is not necessarily welding going on. So this is just to say that winter sea ice and marginalized zone sea ice are posing perhaps slightly different challenges for modeling community. Um, so in just a few words about existing models, because of course, if anyone starts saying that, okay, I have a new model, then the first question is, okay, why the hell do you need to develop a new model? We already have some. And well, the quick answer to this to this question is that I didn't know about the existence of all these models when I was thinking about how to develop a CIS model. It sort of came out as an idea that I had during some talks about um, unrelated to discrete element model in CI talks, so continuous model in CI talks, and I was trying to figure out, well, how one would even approach this problem, and those ideas kept developing, and I'm very thankful to get this project funded by the ONR, such that we can spend more time into developing some new ideas. So, but then of course, at some point we need to come back and to think, well, how is what is the sort of similarities and differences between existing models, and how would our model compare to them? And are there any specific advantages of the ideas behind our model versus the other models? So this is just examples of a few models, and there are more. And during this workshop, I hope to learn a bit more about other models as well. But there are some similarities that I saw, and one of them being that CIS has been modeled as a combination of bonded elements, right? So the idea is that uh, you can there are sort of two types of approaches to this problem, right? So one approach could be that if you assume that sea ice is a continuous media, so you can write down some sort of continuous equations which are very difficult to solve, and then you just using the discrete element as a way of solving continuous partial differential equations that have sort of shocks and discontinuities. So one example of this could be sort of the classical example of smooth particle hydrodynamics. So this is when, let's say, you have like a rock falling into the water, into the surface of the water, and then you have splashes flying out of the water, right? So simulating something like this is extremely difficult with Eulerian grids, because you have this sort of regions of water separating into chunks. However, it is fairly straightforward to simulate such things with particle methods. So with where you prescribe basically forces that act on a particle, and then you see where the particle moves, and then you average forces over many particles to figure out how sort of the whole thing moves. So there's one method like this. So if you it's sort of a pure using discrete elements as a way of solving a continuous equation. So another method, of course, is to say, well, let's suppose that we don't have continuous equations, so we don't know how to write them, and it is eventually our final goal is to write continuous evolution equations for sea ice. But to get to that system of continuous equations, well, we need to sort out how the system behaves at small scales. So at the scales of the so-called flows. And what you want to do is to construct a set of laws, interaction laws between various elements, such that on large scales, the sea ice behaves as it's supposed to behave, right? So you can reproduce the natural motion of sea ice under various types of forcing on large scale well. Um, and various models over here use different, perhaps different shapes. You can have squares, circles, or point particles, or any kind of shapes. I guess from other groups you will see some other shapes as well. But the idea here was that you would create bonds, and those bonds will represent the between the elements. So if you move one element away from another, well, it will represent a sort of tensile deformations, and they can break perhaps, and this would represent fractures. And if you break many of these bonds, say along the line, this would form a lead. Um, in this kind of formulation, we don't really have actual shapes and sizes of flows forming naturally. Um, but so sorry, they don't necessarily have to form naturally, but you could have the formation of flows, where a flow would be sort of a chunk of rigidly bonded particles together, and then this flow will be sort of different from other flows, which are, let's say, either less bonded or not bonded at all, right? So, but each element over here is a sort of fairly shapeless thing. So it could be a sort of more like a water parcel when you're talking about turbulence simulations, where the parcel is it doesn't need to have a shape, right? So it's just there to calculate forces on it and figure out how it moves. So what we want to do with our model is to go a step sort of above the particle description, and to say, well, okay, we want to have a particle which represents an actual physically observed flow, and then we want to simulate the behavior of flow as a sort of a whole full life cycle of it, right? Such that the shape of it comes out as a solution of the model. So this is our goal over here, right? So we want to simulate the life cycle of a physically observed flow. And of course, the hope, as with any sort of small scale model, is that we'll be able to validate this kind of flow interaction rules based on direct measurements at the scale of flows. Of course, it's difficult to do, but that's the goal. Um, so here's the model. So this is, I'm going to explain a small prototype of the model. It's called SubZero. And one of the major advantages of this model is that it uses this polygons for the particles. And polygons have vertices, and you can have a sort of an outline of a polygon, but inside of it, it could be composed out of several other polygons if you want to increase the complexity, or you can just deal with just an outline. And these polygons are non-convex, and I'll come back to it. So it's extremely important for this model to have non-convex. And of course, the engine of any discrete element model with particles is the collisions operator over here. It takes some effort to figure out what the collisions are supposed to be, even if you assume that collisions are, say, purely elastic. In a case of collisions of two bodies like this, it's fairly difficult to do if they are non-convex. But nonetheless, it's possible. So we did that. And this is just one example where we just take two particles at random with random shapes and just smash them one into another, and then plot a sort of histogram of how the energy changes with respect to its initial energy. I'm talking about kinetic energy, which of course involves translational energy as well as rotational energy. Um, and in the case of no damping means here like there's no tangential forces and no dissipation. So it's like supposed to be a perfectly inelastic collisions, and the bar over here, the blue bar, is basically all the, looks like a delta function around zero, but the error over here is not perfectly zero. It's about 10 to the minus 3, meaning it's about 1/10 of a percent error that we have. So that means collisions are working, and if we include some sort of frictional forces, then tangential forces, then you can sort of skew this distribution with orange ones towards dissipation. And if we include sort of extra dissipation to put, closer to perfect inelastic collisions where most of the energy is being lost, then all this distribution can go all the way to the right to -1, um, which is sort of one limit of CI's dynamics, if you wish. Um, what else does the flow model do is it needs to be coupled with Eulerian ocean and atmosphere, because the driving forces are coming from the atmosphere and the ocean, and those models are really not caring about the discrete element features that flow over them, right? So those models are written in a Eulerian grid, so there is some sort of mapping that needs to be done. But regardless of mapping, so we basically have the forces that, Newton's law written for each particle, and we have atmosphere and oceanic drags that come in as surface integrals over the area of the flow. This is done for giant flows, especially relevant for giant flows. Then you have the collision forces over here, and for the torques, you write down same equations. You have atmospheric oceanic torques, and as well as torques associated when each flow is bumping with each other. And of course, for non-convex flows, any kind of two flows bumping into each other will have many interaction points, could have many interaction points, so you got to take into account. And over here, in addition, we sort of make it possible to take into account unobserved flows, because the idea is that just like in ocean turbulence or in atmospheric turbulence, you have a set of eddies or a set of flows which have certain scales that you do resolve, and then you have a whole bunch of scales that you do not resolve, and those unresolved flows statistically will provide some sort of impact on those flows that you do resolve. So we leave the opportunity here to get this interaction going. Um, so a few things to demonstrate. So basically, SubZero physics, the backbone of it is the collision engines. That's perhaps the most difficult part of it, but this can be done. This is what we did, and we're just to mention, we're not really relying on any sort of standard or non-standard libraries for collisions. So this is entirely code written from scratch, and this code basically is aiming to simulate collisions between these non-convex particles. So over here you see lots of shapes of these particles. They're, random, whatever you can think of, right? And this is a snapshot of a marginalized zone sea ice. So that's, for example, just one simulation where you have a whole bunch of flows just sort of advected by a random grid of eddies, and with some sort of oscillatory winds going around. And this is just to demonstrate that the model is sort of behaving as a granular model is supposed to behave. However, this case over here with marginalized zone, where perhaps on short time scales, all these rigid fractures, welding thing, and thermodynamic melt and growth perhaps are not as important, at least on very short time scale, let's say of the order of hours. So you can sort of turn off all the physics in your model and just test, okay, how are various forcings evolving the chunks of ice. So I would say this is the simplest case. Um, this case for the winter sea ice, so simulating a sort of 100% concentrated sea ice is really difficult, and it involves having fractures in sea ice, of course, because if you have many solid bodies connected with each other, well, solid bodies, they basically jam, right? So if you have many particles and you try to shift one relative to another, nothing will move, right? So it's just interconnected pieces of solid bodies. So what ice does is that when stresses become overwhelmingly large as to satisfy some sort of fracture criteria, then each element can fracture and sort of grind down to small, basically dust-like particles, and then the ice can move, right? So a simulation like this, here's an example. This is where we have strong forcing, like in a sense of gyres, and we have one flow in the middle that doesn't move. So it acts as a sort of island over which other flows sort of can collide and break. But eventually, you have many fractures. The flow size distribution is shifting towards smaller and smaller flows, and a lot of flows become so small as to become basically unimportant when it comes to considering collision forces, and then they disappear from the model. Of course, we do keep track of their mass in this case. Um, yeah, so this would be a case of convex flows, which is quite a degenerate case over here, degenerate case over here, because if you look at the beginning of the simulation, oops, let me go back. The simulation started with convex shapes, and then the fracture rules, they were just fracturing the flows on straight lines. And those fractures actually do not change the fact, like they don't take the flows away from being convex. They cannot make it concave because we're using the Voronoi cancellation for fractures over here. So the main issue with these convex flows is that if you have a sort of divergent um, current over here or divergent type forces, all these flows can sort of just be pulled apart, right, without any resistance, or maybe with some resistance, but eventually they can be just moved apart unless they're bonded together, right? With non-convex flows, regardless if they're bonded or not, nothing will move, right? Because if you have some sort of crazy shaped, like puzzle-shaped pieces, regardless if they're bonds or not, if you have divergent forcing, nothing will move, right? So the only way to move is to actually fracture elements themselves rather than destroying bonds. Um, so that means that the actual simulation in our model with non-convex flows actually doesn't require any bonds. And this is what the physical difference is between our model and some of the models that you will hear about during the workshop, is that we don't have bonds. So all the processes here that are usually simulated by means of providing a specific bond, a specific interaction rules via these bonds, we have them parameterized using interactions between the polygons over here. Uh, so for example, things like grinding sharp corners of the flows, well, those are to represent a sort of more realistic shape of flows. This is done via parameterization, where we say, okay, there's some sort of probability of fracture occurring at the corners, and that probability depends on whether or not you collide with those corners. So this would be one case when you can affect the shapes of the flows. Um, another reason why the fact that non-convex flows are essential to our model is the formation of new flows. If we start from, let's say, a low concentrated area, and if you imagine that you're constraining yourself only to have convex particles, well, the holes, the sort of the empty spaces between two or a set of convex regions will be concave, right? And as a result, you will kind of struggle with filling those holes. You would need a lot of, basically a lot of tiny elements. Let's say if you're dealing with circles, right? You'll need to fill some sort of edges over here. Oops. To fill some sort of edges in between these kind of tight domains, you would need to have a lot of elements. But if you have non-convex flows, then you can just have one flow that has, let's say, a shape, which is that bizarre shape of the area, which is exactly how new ice forms, right? So ice doesn't quite care if the area is convex or concave. You just have an open area in the water, and the ice is going to grow in whatever area there is, and that's going to eventually consolidate to become a flow. So this is, I would say, a more natural way of packing the system. But of course, we're exchanging the simplicity of convex collisions between convex particles with uh, sort of the realism of non-convex particles, and the complexity that comes with it. Um, all right, and also to mention that there is a high resolution Eulerian grid that can be coarsened, of course, but over here the representation is such that we can pack the domain to whatever concentration you want, all the way to 100%. All right, so I better speed up because this talk is getting long. So the SubZero physics involves also welding and ridging. Those are done, again, not at the bond level. We don't have bonds in the model, but it is done at a probabilistic interaction rules between polygons level. So the idea is that when you have welding, welding occurs when you have two flows that come together, and we allow for some numerical overlap between the two regions. And then if this overlap, if the overlap area over here is fairly large, then it can trigger welding, provided that thermodynamic conditions are met. For example, in winter, when there's strong sort of heat flux coming out of the sea ice, so we grow in ice. Provided that the two pieces are close together, they will weld. So that welding operation is that if you had originally flow 1 and flow 2, we're going to create this bizarrely shaped flow out of these two. Now, ridging over here, on the other hand, is preserving the same thing. So for the same two flows, which are kind of colliding with each other, we're using a parameterization derived based on experiments for colliding two chunks of ice of two thicknesses and figuring out and using sort of the criteria based on thicknesses to figure out if ridging occurs. So in this case, when ridging occurs, well, if one flow is thicker than the other, then one flow over here will basically absorb the thickness of another flow. So you still have two flows, but one of them will absorb this thickness over here. So it kind of goes underneath and above it. Um, or we can, if the two flows, let's say, are of equal thicknesses, then we can either probabilistically redistribute the mass, or we can split the mass in half and sort of say, okay, one mass goes into one flow, the other mass goes into another flow. In the same sense, we can have lateral melt, we can have thermodynamic growth, lateral melt and growth as well. So we can change basically the polygons if there's ice ocean heat fluxes, let's say, melting it laterally, which is not really that important for big flows, but for smaller flows, it does become important. Thermodynamics, of course, is important for all the flows, and the vertical thickness of the flow is also changing according to thermodynamics. and according to whatever heat fluxes we have from the atmosphere as well as from the ocean. So in this case, we implemented a very simple a single layer thermodynamics, but actually I'm not going to write an equation for the HDT because we can plug in whatever you want over here. So we can have a multiple layers of temperature or whatever complexity thermodynamics model that comes in, because it's just naturally is applied at the level of a single ice flow. So there are no issues with sort of splitting the flows into sort of area versus thickness when the volume is being created. Um, so now just for the sort of the gemstone of this whole um, SubZero simulation, I want to show that the winter simulation can be done. And this is a big question mark, right? So we created some sort of bizarre model of interactions between the polygons, and we call it the ice model. And we hope that all the parameterization that we brought in are somewhat representative of true sea ice. But of course, if mathematics behind such models is is not explored at all, such that, for example, do we have issues of convergence? Like, is it even plausible to run a simulation for, let's say, winter sea ice that doesn't explode in the numbers of elements, that kind of produces realistic flow size distributions? So all of these questions for this type of model are completely uh, unanswered. And but by test, what we can do is we can say that, well, we can run the model and see what happens, right? So even though we at the moment we cannot mathematically answer those questions, we can just demonstrate that it does work. And in this case, I'm just showing you the winter simulation where we start off with some initial conditions, and you have fractures over here. As you can see, various elements fracturing. They're creating open space. This open space is being filled with new elements, such to sustain a near 100% concentration at all times. So it's the sort of winter case. And eventually you generate quite complicated shapes. You see the polygonal shapes are very complicated, and then they somehow resemble a little bit the SAR images that we observe, meaning that, well, sea ice is not like this well-rounded shapes, but it has quite a complicated structure to it. And Brandon is going to show you a bit more quantitative comparison of flow size distribution, for example, of the simulation with whatever we observe from nature, and to say that actually flow that size distribution over here converges to some fairly sort of realistic exponent of minus 1.5 power law distribution with a power of minus 1.5, and that the number of elements can actually not explode to infinity, surprisingly enough. Um, so to summarize, basically, well, we had a model that, I I mean, at least I believe that a simulation like this is a unique one. So I haven't seen any model capable of doing this. There is some I mean, of course, a lot of models that other people have at the model at the moment can be sort of pushed into this regime by using non-convex particles, right? But looks like what we have done, and there's quite a lot of tricks over here, numerical tricks, in order to make the model run, because the complexity of the polygons need to be taken care of, the amount of flows need to be taken care of. So but a simulation like this with polygonal shapes that is producing you as part of the solution the shapes of the flows, and that runs at 100% concentration, it looks like it's quite a unique simulation. And This is sort of the pride and joy of this SubZero um, type of model. Um, all right, so in just future work, there's a ton of future work related to mathematical analysis of this model, because it's completely unexplored how it behaves. But of course, we're looking into improving physics, improving numerical efficiency by coding it using some proper numerical languages and libraries that deal with a giant number of elements. We'd like to also couple this model to the Julia version of the ocean. So this is connecting with the Klima project and the MIT GCM model for sea ice. Um, and I would say that what has been done over the past 2 years to develop this model is quite an effort, and uh, a lot of validation studies are needed to figure out if this model is better or worse, or neutral with respect to other existing models. But definitely it sparked quite a lot of ideas and a lot of implementation type ideas of various processes, like parameterization of various processes, they came to life. So uh, we hope to continue basically developing it into something that can be used, perhaps in a climate model one day. So thank you very much for your attention. It's been a bit of a long talk. I'm sorry about that. And Brandon Montemura is going to check out his talk. So he's going to talk a little bit more about validation examples, or like the process studies that we have done with this model. Um, so thank you very much again. Bye.